Welcome. In today's video, we will solve the exercises 35, 36 and 37 of chapter 2 from book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. We start with question 35. The statement is prove that the set of all 3 cross 3 matrices with real entries of the form this matrix have 1 on the main diagonal and all entries from a lower uh, part of the main diagonal are 0 and the above are ABC are any real numbers, and we have to show that the collection of all this kind of matrices form a group. So we consider that G is a set which consists of this kind of matrices 1 AB 0 1 C 0 0 and 1, where these ABC are real numbers. But we have to show that this G form a group. Okay, first of all, we will define the multiplication. Multiplication of this kind of matrices will be of the form, if we multiply, we consider two arbitrary matrices of the form. First one is 1AB 0 1 C 0 0 1, and the second is 1 A prime B prime 0 1 C prime 0 0 1, and the result will be of the form 1 A plus A prime B prime plus B C prime plus B 0 1 and C prime plus C and 0 0 1. And we see that the product of the two such kind of matrices again is the matrix of same form. So this belongs to G. So first thing is that G is closed under this multiplication. Also, so G is closed under matrix multiplication. Also, we know that in general for the matrices the associative law holds for all. So in this case also the associative law holds. And the identity element, if we see, is also of the form of matrices which belongs to G. So this identity also belongs to G. And we know that if A is this matrix, then A inverse will be, after simple calculation, is 1 minus A, AC minus B, 0, 1 minus C and 0, 0, 1. And that is also of the form of the matrices which belongs to G. So this also belongs to G. So this means G is a group. Okay. The next question is question 36. Question 36 has two parts. The first part is prove that in a group G, AB whole square is equal to A square B square if and only if AB is equal to BA. So the solution is, let consider AB whole square is equal to A square B square for all AB belongs to G. And this means, and if and only if arrow is going on both sides, this means if and only if AB into AB is equal to A times A into B times B. We just expand this one and this one for all AB belongs to G. Now, if we apply A inverse or pre-multiplication with A inverse, we will get for all AB belongs to G. We get BAB is equal to ABP, and this is also if and only if for all AB belongs to G. If and only if means we do not have to prove it the conversely part. Okay. Now we post multiply or multiply from the right side with B inverse for all AB belongs to G. And this is if and only if BA is equal to AB for all AB belongs to G. And this is what we want to prove. Okay, we consider the next part. The part B is prove that in a group AB to raise power minus 2 is equal to B to raise power minus 2, A to raise power minus 2 if and only if AB is equal to BA. So the solution is consider or let AB to raise power minus 2 is equal to B to raise power minus 2, A to raise power minus 2 for all AB belongs to G. G is the group. And this will also go if and only if. This can be written as AB square whole to raise power minus 1, and the same way B square to raise power minus 1 and A square to raise power minus 1, and that is also for all AB belongs to G. And if we expand this, we got AB whole to raise power minus 1, and on the right side B to raise power minus 1 A whole inverse, and that is also for all AB belongs to G. And this will go in the same way if and only if B inverse, if we use socks shoe property, we get this one. And on the right side, it is B inverse, B inverse, A inverse, A inverse. Okay, if we pre-multiply by B on both sides, we get this one, and this is if and only if, and also post multiply by A in the same step. We get this is identity, this is identity, this is identity, and this is identity. What we left is A inverse B inverse is equal to B inverse A inverse. Okay. Now, if we again pre-multiply by B, we get this one, and this is equal to B A inverse B inverse is equal to A inverse. And now, if we again multiply by pre-multiplication with A, this will be A inverse, and this is all for all AB belongs to G. We will get AB A inverse B inverse is equal to identity. And again, if we continue this way and post multiply with B, we will get if and only if AB A inverse, this will be identity, is equal to B, and then again post multiply with A, we will get if and only if AB is equal to B, and that is what we want to prove. So here the proof is complete. we move to the question number 37. Okay. The statement is let G be a finite group and n an odd positive integer. Show that the number of elements x of G such that x raised power n is identity is odd. Show that the number of elements x of G such that x raised power n is not equal to identity is even. Okay, we start the solution. Let A be subset of G such that A consists of all those elements of G such that x raised power n is identity. Now, if we want to show that the number of elements with this property are odd, we have to show that the cardinality of A is odd. We have to show that A has odd number of elements. Exact. Okay. Since E raised power n is again E, identity raised power n is identity, this means this E belongs to A, and so A is non-empty. If A is non-empty, it means, okay, if A does not contain any other non-identity element, then A cardinality is 1 and we have done. But if X belongs to A such that X is non-identity and X raised power n is identity, then also X inverse which with power n is X minus n is equal to X raised power n to raise power minus 1. So E, because Xn is E, inverse which is E. This means X inverse also belongs to A. Means whenever a non-identity element X belongs to A, then X inverse also belongs to A. This means non-identity elements in A will appear in pairs. So number of elements, number of non-identity elements in A is even, and combining these even number of elements with identity, we got, so number of total elements including non-identity and identity elements in A is odd. Okay. Now consider another set, let B in the set of those elements of group G such that x raised power n is not E. And if x raised power n is not equal to identity, this implies that x inverse raised power n is also not identity. So elements in B will be even in numbers because they appear as a pair. So that's all about today's lecture. If this is helpful, then please subscribe the channel and like the video.